All right, this is my new series. I'm starting on the topics of linear regression. Um, and compared to my last series, I'm going to I'm going to try to make some improvements. So I realized that I unreasonably just stuttered a lot of times when I was going through the lecture slides. So I'll try to be a little less hesitant and be more thorough in the mathematical procedures that I'm trying to go through. Other than that, I think we can get started. So one of my videos in the last series, I went through how covariance and correlation were kind of useful metrics to see X's relationship to Y. But despite X and Y, despite covariance and correlation being used to find those two relationships, they don't necessarily measure how X affects Y, or how a specific measurement in X will kind of determine Y's output. So say we have, in a data set, we have X, we have income, and we want to see the relationship on how that affects food expenditure. And so our question becomes, what criteria could we use to, draw the line that you see on the left? And so in our example, we want to express y as a linear function of x. So we see a clear, like a linear trend that's drawn over the graph. That is given by y equals beta 1 plus beta 2 x1 plus the error term. And so this line is actually chosen based on the least squares regression output, short for LS. And so the LS regression, it minimizes the squared error terms. Now I'll quickly get back to what that means later, but just know that for now because that's very important. And so the characters of this function is that the slope given by beta 2, we can also call it the coefficient, the marginal effect, that is given by the covariance of x and y divided by the variance of x. Now, I did go over like how we can calculate these formulas, but we're never actually, like you guessed, like this function, we're never actually going to calculate by hand. It's almost always done on software, so it's good to get an intuitive sense on how the slope is calculated, but we're never actually, the only things we're going to be concerned is like the characteristics of the function, not necessarily the mathematical parts. And then notice how when we're drawing a line through the data points, obviously not all, in fact, most of the data points aren't actually connected to the fitted line we draw. So, and that is how we're going to measure the error term, which is the difference between the actual and the predicted value. So the actual would be the values drawn on the line, and then the predicted would be the values drawn on the line, and then the actual would be the data points given we see here. And so the error term is actually measured by the vertical differences of the predicted and the actual. Again, I'll expand on that later, but it's good to get just kind of a brief intro to what we're trying to do. All right, so in the simple linear regression, and by simple linear regression, I mean this function right here, where we only have one explanatory variable. Beta 1 is not considered an explanatory variable because it's not part of the x. This is just the intercept. So in the simple linear regression where we have just one explanatory variable, we have to make 5 assumptions. And the 5 assumptions, they are given here. Now, the 5 assumptions I wrote down, they're not exclusive to my lecture. They're kind of consistent on like every every lecture or video you'll see through the simple linear regression. So I'll go over them one by one. And so the first one is that it must be linear. Pretty simple. We can't assume that the relationship between x and y is quadratic. So the variable x here, it must be the power of 1. It can't be like a logged form or like a squared. And then the expectation of error must be 0. So what does that mean? Well, obviously we have the errors. Each of these errors within these data points, they're obviously not equal to 0. The error from here to the fitted line here will be a positive error, and then the error between like these values under the line, they'll be negative. However, if we add all of them up, then our expectation, or on average, our sum, we should get a result of 0. All right, and then for the third topic, we have the third assumption. We have what is known as homoscedasticity, which means that the variance of the error must be constant. This is very hard to understand what this means just on top of the head. So I'll go over that visually, but this is kind of an introduction to every like characteristics of the linear regression. So it makes sense if you're not understanding this right away. X and Y's errors must be correlated. Again, easier to see visually. But just in words, the errors must be statistically independent, and then values of the error in one observation cannot be related to values of another observation of the error. And then finally, for the fifth assumption, we say that x must take on at least 2 values, and then the probability of x is all equal to 1. So this is actually, besides maybe the first assumption, the most simple assumption. It's easy to overthink what the x must take on to 2 different values actually means, but it literally just means as long as we have like two x values that have different values, like it's like you don't have to overthink on this one. It's literally just what it says. And then the common misunderstanding is that the x values and its errors are being independent. That's a result of our 5 assumptions in the simple linear regression. That's necessarily not an assumption, but this is like another useful characteristic to know. But it is a result of an assumption, not an assumption. All right, so remember, errors are always calculated by the y differences, as I mentioned before. So if we have 3 x values given here, remember that it's always a vertical differences. So for the first x1 value, we have the y value given here, and then the error is based off the differences here. So not like, we're not measuring like the diagonal differences or whatever, it's just the y-axis. If we draw another fitted point here, we have y2. This we can see as the first error, the second error, and then y3, x3, and then this is the difference here is what we call error 3. So only the vertical axis. This is very important. And so if we try to estimate beta 1 and beta 2 for the regression line, we call this the fitted regression line, where we it looks very identical to the original regression line, except regression equation right over here, except we denote it as b instead of beta, and then we'll give it like a hat on the top. So y hat equals to beta 1 hat plus beta 2 hat xi plus error hat as well. And then again, remember that the error is based off the actual versus the predicted. So this is the actual right here, and then this is what we're predicting based on this equation here. And so error is accounting for those differences that where we're predicting the equation, and then the error is saying, hey, our equation is not perfect. We have to compensate by accounting for the differences of our fitted line. And then this third equation is just expanding on what y hat is, so right here. Okay, so the ordinary least squares, short for OLS, or OLS, short for ordinary least squares, that is calculated by minimizing the sum of squared errors. So what is the sum of squared errors? Well, we learned how to calculate the errors, right? So if we add all of those errors up, or if we square them and add them all up, then then what we will get is called the sum of squared errors. Now, we have to be careful that we must square each of the differences because we want we don't want a negative value, because we want the absolute value of all the differences so that we can compare the sum of squared errors for like different trials of the fitted line to see which of the lines we fit has like the smallest sum of squared errors. If you're asking why, or if you're wondering why we squared it instead of finding the absolute value, we kind of do that to be able to like differentiate the sum of squared errors. So if we like differentiate this exponent, this 2 at the exponent will be like a 2 in the coefficient. But overall, it's kind of like a way of inflating our error so that we can be more sure of we can be more safe of our fitted line. And then visually, this is a good example of if we have like a y fitted here that minimizes the sum of squared errors, right? Compared to other fitted lines like y2 and y3, the sum of squared errors, they don't minimize the sum of squared, or the y2 and y3, because they don't give a good fitted line based on the data points. Our beta 1 and beta 2 for y2 and y3 are not going to be as accurate. And therefore, the sum of squared errors for y2 and y3 will most likely be greater than the y hat value of the function that minimizes the SSE. All right, so let's give another example here. Hold on. Okay, let's do one example here of a real life example. So let's say for income and food expenditure, our sum of squared errors becomes the lowest when we have this function right here. So again, we will never actually have to calculate this. It will always be calculated by software. But let's say we have an income of 100, and based on that income, we want to know our average food expenditure. Keyword average. Again, we don't know that the y value for our result based on our income is going to be 100% correct. So it's going to be around or on average around that. But if our income is 100, then we can simply just substitute the 100 into the x. So 10 times 100 plus 50, which is 1050. And then we can say that the 10 acts as the coefficient or slope, or the marginal effect, as I said. And to give a good example of that, let's say that our income increases to 101, just by 1 unit. And then the question is, what would our new food expenditure be? And what is the difference of the impact from the change of the income? So what is our difference of the impact of y just by increasing the income unit by 1? Okay, so if we do that, then we can rewrite the equation of y hat equals 10, 101 plus 50, which is given by 1060. Since our previous example is 1050, right, our difference becomes 10 from the increased income of 1. And we can see that from the slope. As we increase the slope by 1, or as we increase the unit of x by 1, our y value, it'll increase by the slope here. And so mathematically, I can demonstrate, we can say that the expectation of the output, given that the x unit increases by 1, minus when our previous x value, right? So if we're calculating the difference of that, we can write that mathematically out. And so notice that the only difference is x plus 1 compared to x. And so if we expand that equation, we get plus beta 2 minus beta 2 and then minus beta 2x. And so if we cross this off, we only get a result of beta 2. So again, mathematically, we're demonstrating that a change of, or an increase of 1 unit of x will cause a 10 unit increase of y. And then we can also say that for the difference, if like our income decreases to 99, then our food expenditure in this case will also decrease by 10. All right, that's going to be it for the first video of linear regression. I'm going to continue this concept further in the next video, so stay in touch with that.